Hello again, time for another one of those requested revisions. Got asked about radiation interactions with matter. Sounds potentially quite complicated, but not all of it is in the A-level course. So, down there, standard electromagnetic spectrum as covered by pretty much every year group in secondary schools, I would say. And they all have an interaction where they cause something to happen within substances, matter, hence the title. Now those four things there are the things that you can cause. Movement, or moving. Also referred to unnecessarily complexly perhaps as translation. It's a mathematical term for moving something. Rotate, I think we all know what rotate means. Rotate literally means what you think it means, but the particles do have to be in a fluid in order to rotate. They don't rotate in a solid, they're fixed in position. A bit like you can't move if you're fixed in position in a solid. Vibrate, that's something that bonds will do. So what happens is that you can think of it as one atom and another atom with a bond, and the distance between them changes. That's the vibration. There are some criteria that mean that that sometimes happens, sometimes doesn't, but that's not in the scope of what we do today. And finally, electrons, and you can send electrons up or you can bring them back down again. That's not an electron pair in opposite spins. That's electrons going up or electrons coming down. This one here, flame colour, that one there, absorption spectrum, which I covered in a video a few weeks ago. So you can always go back and have a look at that if you want to know more about that. So what we're looking to do is link to what they do there. Now these are increasing energy as you go down there. So radio waves have the most subtle interaction with matter. Gamma rays have the most violent or the most extreme interaction. For gamma rays take matter apart up to a point, they knock electrons right off. Now what you have, if you ignore gamma rays, because I don't know how gamma rays are used, all of these are used, with the exception of gamma rays, as a technique to discover information about matter. So we'll be going through all of those. Some of the ways that these are used are year 13, some of the ways you already know about. So we're just going to link all those together. But I need to get the board sorted out, so I'll see you in a moment. So, that list, just run through what we use them for. Mention some of the things that are outside the scope of the A-level course as well. So, starting with the least energetic, radio waves. Radio waves, very small amount of energy. All it's capable of doing is interfering with the way the nucleus is existing. That gets discussed as nuclear magnetic resonance spectroscopy, or NMR. And in the A-level course it refers to the use with carbon-13 and with hydrogen, and there are reasons why it's those two and why lots of atoms don't do it, but that's again not in the scope of what we're doing today. But radio waves have an interaction with the nucleus of, not all, but a number of atoms. Microwaves will rotate species of various things. Microwaves do that to water, which is how you heat water up in a microwave, because that's what microwave ovens do in the kitchen. Infrared, now I've put an IRS, that stands for infrared spectroscopy, and that is all, like I said just now, about bond vibration. So it's about changing the separation between atoms, and you get the the right energy, it will make it do that. Now that brings to mind something that's common across all of these, and that's this word here, quantise. Now I have quite difficulty explaining quantise to people. Energy can be any value in terms of the number of joules, any number of joules. And light coming from the sun pretty much contains the entirety of all the joules available for a photon of energy. But quantised means that only the exact frequency, now of course, depending on your course, it's one of those two equations. They mean the same thing. Energy is Planck's constant multiplied by the frequency, and there were two symbols for frequency depending on which course it is. And that there tells you that if you know the frequency, you know the energy, but that means that only certain frequencies do things to particular atoms. Now, is that precise? So you get the right frequency for a carbon atom, it will do something. If you get the frequency slightly wrong, it will just sit there and do nothing. And that's what quantised means. It means that when the energy matches the requirement of the atom, something happens. If you don't match it, there is nothing to take place. It's like the electrons jumping between energy levels. That is an example of quantised, where the energy difference between one energy level and another is an exact number of joules. If you put in that exact number of joules, the electron will jump up. If you overdo, it will go higher, providing it matches higher. If it doesn't quite match one of the jumps, it won't do anything. Quantised means you have to match the energy to the required change that you're going to see. So as you go down here, I got to infrared. Infrared spectroscopy means you match the infrared radiation to a bond, and the bond will start doing something. Most of the time it's about bonds changing distance. Sometimes it is actually about a wagging movement, which I love. I think that's quite a good thing. And then sometimes it makes circles of atoms get bigger and smaller. It's called breathing. Most of the time it is just about stretching a bond out. And there are certain bonds that do this. Basically it's any bond that's got two different atoms on one end or the other. It's kind of it, although it's a bit more than that. When you get to light, we had a video like I said a few weeks ago about that, about emission and absorption spectra tied into flame colours, because flame colours are emission spectra. And so when you're talking about using it as a tool, nuclear magnetic resonance spectroscopy, this one here is not in the A-level course. It's called Raman spectroscopy. That's one of the types of it. I only did that at university myself. Infrared spectroscopy is in the A-level course. NMR, yes. Infrared spectroscopy, yes. Absorption and emission spectra, yes. Now ultraviolet does have a spectroscopy type associated with it, but it's not in the A-level course. But what we do know about ultraviolet and the way it does things is it promotes electrons because some elements have no flame colour, and bond breaking because we've done homolytic and heterolytic bond breaking. X-ray crystallography used to be in A-level courses. It's about the positioning of atoms. It's how X-rays interact with electrons around an atomic centre or a nucleus. And I said already, gamma rays ionise, and they also cause DNA damage by virtue of that ionisation, so they rearrange structures. But that is what we do. So at A-level, that, and that are the ones we have to focus on. I'll see you after the edit. So, thin the list down a little bit from the last bit. Just about what we do with them in terms of our A-level courses. NMR gets used for deducing structures of organic molecules. It's incredibly clever, and you can deduce quite a lot of information from what seems like hardly any knowledge or hardly any pieces of collected data. It's one of the things, it's a year 13 skill, and it is traditionally one of the difficult things at A-level people to get their head around. But once you crack it, it's really satisfying because it's a problem solving. It's a sort of problem solving strategy technique. So, not going to do any of these in detail, but that's a year 13. Infrared spectroscopy. It says there what it does. there are, in A-level courses, a data booklet, and one of the things in the data booklet is a set of information about infrared. It contains loads of information, but almost all of the questions are restricted to very few of those things that are listed in there. And those things that are listed in there are they are the energies, they are the frequencies, but the units are just strange, centimetres to the -1. But what you do is you look at an infrared spectrum and you use it to go, oh, that there matches where it should be for a carbon to hydrogen switch. So you go, it's got carbon to hydrogen. As you might imagine by that, organic is the focus for this, like it is for there. So a lot of the deductive skills associated with, I don't know what this compound is, here's some spectroscopic data, is these two things here. So the infrared tells you two atoms that are joined together. Nuclear magnetic resonance tells you about the internal carbon chain, or the hydrogens that are attached. But you'll need to be taught that a different time. Said about this already, I'm not going to go into that. Absorption, emission, flame colours, another video on that already on the YouTube channel. Have a look, or you already have. Mentioned already ultraviolet. I didn't mention the word homolytic. Homolytic meaning one electron goes to one end, one electron goes to the other end. You don't form an ion, you form free radicals, so you get bond breaking in free radical substitution. That's the A-level context of ultraviolet in that respect. The only other thing is, you find it in magnesium and beryllium don't have flame colours. They don't have flame colours because they do have flame colours, but they're ultraviolet and your eyes don't detect them. So they have non-visible flame colours in that context. I've put X-rays back on, I didn't ring it on the last little bit, but you will sometimes see what are called electron density maps. They are like circles around, and they say, oh, that's sodium or chlorine or chloride or whatever. And it's got a number of rings around it. The more rings it has around it, the more electrons it's got. And it's because of the interaction of X-rays with electrons allows you to pick up where those electrons are and draw contour line maps where at the centre is the nucleus. So you see electron density maps. You also, it's how we know the crystalline structure of materials. Now you might go, oh, crystalline structures, they all look the same. No, they don't. There are 32 different types of crystal, which is a surprisingly small number in some respects. And it allows you to look at where the atoms are, the separations, which ones are next to which one, and that allows you to do that. But it, in terms of the structure, but it is again an interaction between electrons and X-rays, because the higher energy things start to mess around with electrons. Ultraviolet pings electrons apart and breaks bonds. Halogens is the context for A-level. X-rays identify where electrons are en masse. And that's kind of it, really. That's putting those interactions in context. It's not going to go into them in any detail. That maybe is a thing for another day. Although I would say that's quite a long video. That would be hours long. This not so. Done this already. There we are. So thank you for watching. I hope that clears up some of the things that resulted in me being asked. Could we do that? Don't forget, I have got now 2 books published. I'll be delighted if you could purchase them. I haven't got one here today. I'll see you soon, because there's another one of these videos in my head that I need to do. So I'll see you for that video very soon. Bye bye.